Welcome. This is not a presentation about another coding agent. Most developers already know that AI can write code, summarize logs, or generate commands. The question I want to focus on is what happens around that intelligence. Where the process lives, how context survives, how tools are connected, how command execution is controlled, and how work becomes observable. Agentic-Nets is a runtime for exactly that layer. It combines AI agents, deterministic automation, tools, humans, and persistent state. In this talk, I will first build the mental model from simple Petri-net concepts, and then go deeper into deployment, MCP, command execution, NetHub, runtime agents, and finally safe team as a running reference application. Let me start with the developer problem. Imagine a production or test instance behaves strangely. A developer finds the instance, checks OpenStack, collects logs, analyzes them, checks Jenkins, inspects the source code, prepares a hotfix, runs tests, and eventually presents the result for review. Today, this process often exists as a combination of personal knowledge, Confluence pages, Jenkins jobs, shell commands, copied log snippets, and AI chat sessions. A normal AI assistant can help with single steps, but it usually does not own the process. It does not automatically remember which context was already collected, what was approved, what command ran on which machine, or what should happen next. Agentic-Nets is aimed at that missing middle layer, making the process itself explicit, executable, inspectable, and reusable. So what is Agentic-Nets in one sentence? It is a runtime where deterministic processes, AI agents, tools, and humans operate over persistent state. That framing is important. The LLM is not the architecture. The GUI is not the product. The runtime is the product. A step may be AI-driven when judgment is required, or deterministic when we already know exactly what should happen. A human may approve a branch, a release, or an infrastructure action. The process state is not hidden inside a prompt. It lives in places and tokens. And the event history records how that state came into existence. This is the foundation for observability and also for later process improvement. Let me clarify the runtime hierarchy, because this can otherwise become confusing. Agentic-Nets is not one diagram. The model ID identifies a durable runtime scope. Inside that scope, sessions are working containers for nets. A session can contain multiple live nets, persona nets, tool nets, runbook nets, test nets, and imported NetHub packages. These nets are not just drawings. Once deployed and started, there are live structures with runtime places, tokens, and transition state. The especially important idea is shared places. Nets can cooperate through places that both can read from or emit to. A persona net can hand work to a tool net, and a team net can call a smaller diagnostic workflow. This is why the system becomes flexible. You can start small and keep composing. Now, for the mental model. A place is persistent state. A token is a work item, a piece of context, or data. A transition is something that acts. The important part for developers is not the mathematical theory. It is that the process becomes explicit. In a normal script, state is hidden in variables or files. In a chat, state is hidden in the conversation. In Agentic-Nets, state is represented as tokens in places, and transitions consume and emit tokens. That gives us a visible process. A trivial example is problem to diagnosis. A problem token enters an analysis transition, and a diagnosis token is emitted. The same idea scales to command execution, Jenkins analysis, hotfix workflows, and entire teams. There are 7 transition types, but the reason this matters is not the number 7. The important architectural point is that AI and deterministic execution are first-class peers in the same process model. Pass routes a token. Map transforms data. HTTP calls an API. Command executes local or remote commands. Link connects or queries knowledge. LLM makes a bounded model call. An agent performs iterative work with tools. So an Agentic-Net is not a chain of LLM calls. It can use deterministic execution for the predictable parts, and AI only where reasoning is genuinely useful. That gives better controllability and a path to reduce LLM cost over time. The editor can make the system look like a visual workflow designer, but that is only the beginning. A transition has topology, where it sits and which places it connects. It has an inscription, presets, action type, emit rules, and execution semantics. Then it must be deployed. Deployment binds it to a runtime lane or an executor. After deployment, it can be started, scheduled, or fired. During firing, it consumes tokens from its presets, executes the action, and emits results to its post sets. This separation matters because the same topology can be retargeted. You can change an inscription, move execution to a different executor, or import a net into another session, without thinking of it as just a static diagram. A net is not a one-shot diagram. It is live. Places can contain work and context. Active transitions can pull, run on a schedule, or react to available tokens. The GUI can show what happened before, what is running now, and what will be scheduled next. Console output and execution results are attached to the runtime story. This is very different from running a script once. The process can live, wait, resume, and be monitored. For developers, that means recurring operational knowledge can become a runtime structure instead of staying a mixture of manual steps and chat sessions. Transitions can also be hosted in different ways. The net topology is stable. It describes places, arcs, and transitions. But transition execution can live in different lanes. Some transitions run in the master lane. Command transitions are intentionally routed to executors because scripts and infrastructure access often need to run close to the target environment. And AI lanes can be delegated or supplied by a connected client, depending on configuration. That is an important architectural property. You don't have to redraw or redesign the net to change where a capability lives. You change the runtime binding and the deployment. Now to one of the strongest unique selling points. Agentic-Nets is not only operated through its GUI. MCP can be the primary control plane. A capable MCP client can create a model, create or select a session, import or build nets, create places and transitions, set inscriptions, deploy transitions, create tokens, fire transitions, query runtime state, and inspect history. Studio is only one control surface. Claude Code, Codex, an IDE agent, or custom automation can operate the runtime directly. For developers, this is very powerful because you can use Agentic-Nets as a persistent execution substrate from the tools you already use. An MCP works in both directions. First, external MCP clients can control Agentic-Nets. Second, an agent transition inside Agentic-Nets can itself consume MCP tools. That means an agent transition can use a GitHub MCP, a browser MCP, a Jenkins MCP, or even the Agentic-Nets MCP itself. That is the dogfooding angle. A net can use the same protocol to inspect or modify nets. So Agentic-Nets is not just an MCP server and not just an MCP client. It is a runtime where MCP capabilities become governed process steps. The value is that MCP tool use is not hidden in a temporary chat. It happens inside a persistent net with visible state, emissions, and history. Here is a subtle but very strong point. The runtime does not need a server-side LLM to be useful. It can run purely as a process runtime. Deterministic transitions execute. Command transitions execute. Tokens and events are stored. MCP clients can create, deploy, fire, and inspect the system. For LLM or agent work, a connected MCP client can provide the intelligence externally. This separates the stable runtime from the AI provider. In other words, the runtime remains valuable even if the model lives outside it. That makes the architecture a good fit for environments where server-side LLM configuration is sensitive, expensive, or simply not desired. Command transitions are one of the most practical features for day-to-day operations. They let the net execute scripts or commands through a remote executor. And here is the important security and architecture point. The executor is placed where the capability exists, and it pulls outward for work instead of exposing inbound APIs. That makes it suitable for Jenkins diagnostics, OpenStack tooling, server commands, repository operations, test environments, or even bounded headless CLI calls, such as Claude Code. The runtime keeps the process context, the permissions, the command token, the result, and the history. The executor provides controlled hands. This is much more than asking an AI to suggest a command. Tooling exists at several levels. A tool does not have to be a simple function call hidden in an agent prompt. It can be a toolnet, meaning an entire reusable process. It can be a script executed through a command transition. It can be a Dockerized tool with an isolated runtime. Or it can be an MCP tool provided by another system. And all of these combined behind the same place, token, and transition model. That gives you a spectrum. For a simple deterministic task, use a script or a map transition. For a reusable workflow, package a toolnet. For external systems, use HTTP or MCP. For infrastructure work, use command transitions and remote executors. This is the tooling story developers need to understand. Another practical point: large artifacts belong outside the model context. Command execution and diagnostics can produce huge results. Log bundles, archives, screenshots, reports, binaries. You do not want to push all of that into an HTTP JSON response or into an LLM context. The process state should remain small and structured. So the large artifact lives in blob store, while the token carries metadata and a URI reference. A downstream transition can then decide whether to summarize part of it, archive it, send it to a developer, or use it as evidence. This keeps the net scalable and avoids turning every transition into a context window problem. Event sourcing is one of the most important differentiators. The runtime does not only store the current state, it stores the events that explain how the state came into existence. When a node is created, a token is emitted, a transition fires, or runtime state changes that produces durable evidence. A red model is derived from that history, and the system can later replay or investigate it. This is stronger than ordinary logging because the history is part of the model of the system. For process improvement, this is extremely valuable. It lets us ask which transitions ran often, which agent decisions were expensive, which paths caused errors, where manual approvals block flow, and which patterns could become deterministic. With event source state, observability becomes historical. We can inspect the current runtime state, but we can also ask why it got there. Where's the token now? Which transition emitted it? Which input and context did the agent see? Which command ran on which executor? Which artifact was produced? Where do failures and retries accumulate? For an operations or development environment, this is a very different level of traceability than a normal AI chat, and it is the basis for optimization. If a certain agent transition repeatedly performs the same steps, the history will show that. Then we can decide whether to redesign the process or crystallize part of it into deterministic execution. Crystallization is probably one of the most powerful ideas in Agentic-Nets. We use AI to discover a process when the process is unclear. The agent explores, reasons, uses tools, and solves the problem. Over time, the event history shows which parts are stable. Those stable parts can be extracted into deterministic transitions, a map transition, an HTTP call, a command transition, or a reusable toolnet. That reduces cost and increases predictability. The key sentence is this: use AI to discover the process, use history to understand it, and crystallize what no longer needs intelligence. The long-term goal is not to pay an LLM forever for repeated behavior. NetHub is not just import and export as a convenience feature. It turns processes into portable software artifacts. A net package can include topology, inscriptions, metadata, seed tokens, and tool descriptors. It can be published, versioned, discovered, and installed. The install target is a model and a session, so a ready net can be injected into an existing runtime context. That gives enormous flexibility. A Jenkins diagnosis net can become a reusable package. A log analysis toolnet can be installed into a team. A persona net can be reused. Eventually, a whole team pattern can be transferred. In practice, this means a small successful use case does not remain a one-off experiment. It becomes an installable operational capability. Applications are another important layer. Agentic-Nets does not have to expose a Petri-net editor to every end user. A dedicated application can use nets and sessions as its backend. An incident console can create incident tokens. A persona chat can talk to a persona net. A workflow form can start a process. A dashboard can show next actions and history. Underneath, the net holds state, approvals, command results, and a process logic. This is important for productization. We can build user-friendly applications where the operational behavior is still governed by explicit nets, rather than hidden in ad hoc backend code or prompts. Runtime agents change the role of the GUI. The GUI is not only a manual editor. Agents can help observe models, monitor active transitions, analyze errors, explain why a token is where it is, build places and transitions, modify inscriptions, deploy transitions, and suggest improvements. This connects directly to MCP and Crystallization. If the runtime exposes its own model as tools, then agents can help improve the harness itself. A runtime agent could detect repeated manual steps and recommend turning them into a deterministic toolnet. This is where Agentic-Nets starts to become more than automation. It becomes a process runtime that can be operated and improved by agents. Before we look at SafeTeam, one more idea. A persona is a net, not just a prompt. A persona net can have an inbox, a planning step, tool execution, review, memory places, result places, and handoff places. The role is embedded in process structure. The context is not only in a hidden prompt. It lives in persistent places. The tools are not just names. They can be command tools, MCP tools, or toolnets. This is why SafeTeam is more than a list of agents. Product manager, architect, developer, QA, and DevOps are process structures with responsibilities, state, and handoffs. SafeTeam is a reference application built on Agentic-Nets. It models a software development process with specialized personas: a product manager, an architect, a developer, QA, and DevOps. The important point is not that there are several agents. The important point is that their work moves through visible places and persistent handoffs. It integrates with surrounding systems: a forum, open project, Git, a remote executor, and a monitor. So SafeTeam demonstrates composition, multiple persona nets, tool nets, and integrations running as a live software development system. SafeTeam is not the minimum use case. It is evidence that the runtime can scale. For the end-to-end story, we follow one token. A feature or an incident is reported. The product manager refines the requirement. The architect shapes the solution. The developer implements through an executor. Build and tests run. QA reviews. DevOps deploys. And feedback returns to the team. Following one token keeps the story understandable because you always know what you're looking at. And the main thing to notice is not that agents produce text. The main thing is that work moves through visible places, state is handed off between roles, deterministic steps and AI reasoning coexist, and the monitor shows the process, not just the final output. Let me close with small, practical first experiments. We should not start by modeling an entire software organization. We can start with a Jenkins assistant that inspects jobs and summarizes failures, or an OpenStack and logs workflow that finds an instance, collects diagnostics, and correlates logs, or a hotfix workflow that analyzes an issue, prepares a branch, runs tests, and presents a patch, or workflow memory, storing runbooks, context, and approvals as reusable process state. The best first experiment is probably low risk and read mostly. An incident is reported, collect logs, analyze, check Jenkins, present the findings to the developer. That validates the runtime, the context, the executor, and the observability without giving the system too much authority too early. Thank you.